Section 6.4, our last section of new material, is first order linear differential equations. So we're going to start with definition. What does that mean? A first order linear differential equation is an equation of the form dy dx plus p of x times y equals q of x, where p and q are continuous functions of x. And this is the standard form of such an equation. All right, so what we're going to do is we're going to be able to solve this type of equation as well. So we've solved separable equations, separable differential equations, and we've solved homogeneous differential equations. And now we're going to solve first order linear differential equations. So the way in which we're going to do that is to first put it into standard form. After it's in standard form, we are going to identify p of x, and p of x is going to be exactly what's multiplied by y. That's how we're going to identify it. And we're going to integrate it, and then we're going to let u of x equal e to the antiderivative of the p of x dx. Okay, so whatever we integrated, what we got on number 2 is going to be the exponent on e. That's what it is. And then we're going to integrate y equals 1 over u of x, integral of q of x, u of x dx, to find the general solution. It does feel weird. It's okay. We're going to do some examples. It'll feel less weird after we've done a few of them.
I feel like this chapter isn't as straightforward as the integrals chapter.
Okay. That's fine. That's okay, right? Not everything is as straightforward as other pieces in mathematics. That's all right. All right. Does everybody have the details written down? Anybody still writing? Okay. So we're going to solve the first order linear differential equation. The first step said that we're supposed to put it into the standard form, and the standard form looks like the derivative plus p of xy equals q of x. So on this one, we have the derivative minus something times y, and it equals whatever's left. So it's already in the right form, correct? Okay. So our first, step here, oops, I went back far too far, was to put it in standard form, and it's already in standard form. And that happens a lot in math. The first step is put it in standard form, it's already there. Okay. The second one is to identify p of x and integrate it. And we said using this standard form version, or this version of the equation in standard form, that p of x is simply what's next to y, the value that's multiplied by y. So what is p of x in this equation? So this is already step 1. Step 2 is to identify p of x. What is p of x? Close. It's -1. It's -1. Just for the good measure, we'll do it in here in a minute. Use it here in a minute. What is q of x in our standard form here? It's actually the 16. We'll use that in a minute. It's not really part of step 2, but step 2 included, whoops, there we go, integrating p of x, right? What is the integral of this? Negative x, right? Okay, so step 3 is to identify, oops, I keep going back too far today, u of x is e to the integral of the p of x. So in our case, we did the integral of p of x, we got negative x, so u of x is e to that value. So u of x equals e to this value, negative x. That's u of x. No, we don't need plus c for what we're working with. We just need the standard without the plus c. We need a version of it, not the general form. And then the last step, step 4, is to create this sort of awkward looking equation. Y equals 1 over u of x. So what is u of x? Well, it's e to the negative x, right? Times the integral of q of x, and q of x we identified was 16, times u of x, which we already used once before, which was e to the negative x dx. Okay? It's not a hard antiderivative, right? Again, we've talked already once before about the fact that the antiderivatives in this section are not as complicated because they come before Chapter 8, where we got all of our just plethora of formulas and rules and ways of doing things. So they're a little bit simpler. So this is 1 over e to the negative x. All of this is multiplied by what comes next. So what is the antiderivative of 16e to the negative x? That is right. So why is there a negative in there, Abby? Yeah, this is really like a u substitution problem, right? Really simple when the u is the exponent negative x, so we do get a negative as part of our antiderivative. And there is a plus c, which we do need on this. Okay? It's not going to make it as complicated as you think. It's still pretty simple. So fret not. I'll make this a little bit smaller.
I'm sure e to the negative x is going to cancel.
They are. So when I distribute this, you're right. I'm going to be left with a negative 16 on the first part, but I'm going to be left with a 1 over e to the negative x times c for the second part. And there's probably a cleaner way to write that, don't you suppose? You put the c on top, but there's even a cleaner way to write it than that.
Oh, yeah.
C e to the x. Because e to the negative x, you can pull it up to the numerator and make it a positive x. So this is the solution of this linear, first order linear differential equation. 16 plus c e to the negative x. And if you don't like the 16 in front, put it minus 16 in back, whatever. Well, it was negative originally down here, Levi. Negative x in the denominator, and then we moved it up to the numerator, it became positive. Yeah. Okay, so that one wasn't bad, right? Okay. But we got more space on the next page, but look, it's not like filled in or anything. All right, so it's going to get a little more complicated because we had a very simple first order linear differential equation to start with. And we always get a little more complicated as we move. That's the whole point. Okay, so step 1 was what? Put it in standard form, and this one is not in standard form. Oh, not at all, yeah. So the first thing we need to do is to kind of get it into standard form. So my first suggestion would be to move the dy to the other side. You all good with that? What would you do next? Divide by the dx. So you could probably do that in the same step if you prefer. I'll have it written in 2 steps on mine. All right, so that's part of it. I mean, having the dy dx or y prime in there, right? What else should I do or could I do? What's next? Distribute. So this would be y cosine of x plus cosine of x equals dy dx. Now what? Maybe I should write standard form down just so that we have a reference from on this particular slide. Let me do that. Our standard form looks like dy dx plus p of x y equals q of x. Right, we need the part that's got the y in it to be subtracted to the right-hand side. So I mean, it's all, I'm going to I'm going to have it exactly backwards of the way that's written over there, but you guys are good with that. So this is cosine of x equals dy dx minus cosine of x times y, or y cosine of x. Okay, so that's step 1. It's now in standard form. Well, it's flipped around from standard form, but we're pretty much there. What is p of x? And just while we're at it, we'll say what q of x is as well. It's negative cosine of x. What is q of x? It's actually cosine of x. Yeah. Okay, good. All right, so now we're going to integrate our p of x. And what will we get when we do? What's the antiderivative of negative cosine of x? It's negative sine of x. All right, so I'll write my equation set up for u of x on this slide, and then I'll move to the next slide for some more space. I think I've got more space. If not, I'll shrink some stuff. How do I create u? E to the thing I just found, right? In this piece right here. So e, in this case, to the negative sine of x. Everybody good with that? Let's see if I created a slide. I did. I was definitely thinking ahead. Sorry about that. U is e to the negative sine of x. All right, so our form that we're supposed to be getting for y equals, this is step 4 now, is that we have y equals 1 over, you know what, let me just write it down generically so that you can see it. This is 1 over e, make sure I've got all the details the way they've got, u of x, integral of q of x, u of x dx. This is what we're identifying into pieces. All right, so we had said that this is y equals 1 over e to the negative sine x times the integral of what? Cosine x e to the negative sine of x dx. Very nice. If you like, we could rewrite the piece on the outside a little bit differently. I think, let's see, I don't have it written differently in my notes, so I guess we'll just leave it. 1 over e to the negative sine of x, probably because it'll cancel something else later anyway. What's going to go on inside here? Yeah, there's a u substitution, and I've already used the letter u in this problem, so let me use something else. What do you want to use? Z. All right, so we'll use a z substitution. What would z be? Negative sine of x dx, or negative sine of x, and then dz would be negative cosine of x dx. Derivative of sine's cosine, so since there's a negative on there, there'll be a negative on the sine, negative on the cosine as well. All right, so identifying those pieces, this will be replaced with an integral. I've got a negative sign, and then I have e to the u du. Oh, I'm sorry, yes. Have it there. E is e to the z dz. Thank you. All right, so what's the antiderivative of e to the z? E to the z. So I have a negative e to the z, and z, of course, is negative sine of x. And then I have a plus c here. Don't forget the plus c here, otherwise everything cancels out to 1 every single time. That's the way it works, okay? Or at least to a constant, maybe not to 1, but to a constant. So when I distribute this through, we definitely get, in this case, a negative 1 at the beginning, right? Plus 1 over e to the negative sine of c, sine of x plus times c. Get my details in there written right. So I have negative 1. What's a simpler way to write what's there? C e to the sine of x. That's my second solution of the day. Okay. If you guys see any of my Calc 1 students, please tell them that it's very important that they learn their trig, right? Yeah, there's still some of them struggling with the trig ideas, but you guys seem to have had that one down pretty well, so tell them it's important. All right, we have one more example. This is the last example that we're going to do all together like this. So last example. We'll see. It's a messy looking one, and it actually says find the particular solution. What in the world does particular solution mean? Solve for c at the end. So it's going to have an extra step on the end of it that's going to use the y of 0 equals 1 part, right? Yeah, that's easy. It's no big deal. We've done that hundreds of times. No big deal. All right. But come on now. Where does this problem start?
Is it standard form?
Yeah, but what do you notice, Abby? It's in standard form, right? Do you guys see that? This one's already in standard form, so we skipped the first step altogether. Step 1 done. It's already in standard form. Step 2 is to identify p of x, and I'm sort of throwing q of x in the mix there just because it's helpful to have already thought through it. What is p of x? Tangent of x. And just for good measure, what is q of x? Secant x plus cosine of x, yes. Okay. So then, what is the antiderivative of tangent? And that's one that is on your sheet. It's not one we see used very often. So you might want to grab it out if you don't remember it. What's the antiderivative of tangent? There's a negative. Natural log. Very good, Jaden. Yes. And then plus c normally, yes. Correct. It's the negative natural log of the cosine of x in absolute values. So step 3 is to identify that u of x is e to this wonderful, beautiful negative natural log of the cosine of x. By the way, there are some books that will not use this form of the antiderivative for tangent. Any idea what else they might use that's equivalent to this? And they actually use the natural log of secant. Why would they do that? Or why would that be the same? Yeah, the negative in front, they move it to be the exponent on cosine. And if you have a negative, the cosine to the -1, that's the same as the reciprocal, so it becomes secant. Just so that you're aware, if you were to see another book, or if you were to Google something online and you see that showing up in there, it's not necessarily wrong, it's just a different approach to thinking about it. Okay. All right, so we have our u of x. So I think we're ready to do step 4. So we have y equals 1 over e to the negative natural log of the absolute value of the cosine of x times the integral of q of x, which is secant x plus cosine of x, times e to the negative.
Does that have to be a plus c? Yeah. Oh, we don't have it.
Not yet. We haven't integrated yet. Well, we did integrate for the u of x, but we don't do plus c on that part. We leave that off. Yeah. And then I need e to the negative natural log of the absolute value of cosine of x dx. What a mess. But some very interesting things are going to happen. U substitution is not as particularly helpful on this. If you let u be the exponent, negative natural log of the absolute value cosine of x, kind of like we did in the last problem, you don't get secant x plus cosine x. In fact, you get tangent, right? You know you get tangent because that's the antiderivative of the value that we started with, tangent. So that's not going to be useful on this one. However, you should notice that you have an e raised to a natural log almost, right? So if you were to take this negative up, as I suggested, as an alternate form or view of doing this, you would have the e and the natural log in the right sort of relationship in order to cancel them. So this is, yes, so e to the negative natural log absolute value cosine of x. Let me rewrite with pieces I don't have to have here. This is secant x plus cosine of x. And if I move the negative up, I will have e to the natural log of secant of x. And these will cancel somehow. And, they cancel each other out in terms of their operational status. And I'm going to be left with simply secant. So now I would have 1 over e to the negative natural log of the cosine of x times the integral of secant of x plus cosine of x. All of that, I've been sloppy with my notation, those should be in parentheses, multiplied by secant of x dx. Beautiful things are going to happen with that piece that's underneath or inside of the integrand. Did I go too fast?
Yes, you did.
I'm sorry. I'll go back,
No,
Levi.
no, you're good.
You got it all?
Yeah, I got it.
Okay. The first part, and I'll copy it to the next slide, in fact, to be easier. First part, of course, stays the same, 1 over e to the negative natural log absolute value cosine of x. What goes on inside of our integral?
You're going to get secant squared of x, and then cosine.
Okay, so what is cosine x secant x? Yes, indeed, this is 1. Why? They are reciprocals.
Which isn't that just tangent?
Yes, ma'am. So now I have secant squared of x plus 1 dx. And that is tangent of x. Hang on a second. Something weird written down. Okay, so I have e to the negative natural log of absolute value of cosine of x. This is not exactly tangent, and I don't actually think that that ends up being helpful to know. Secant squared of x plus 1 is a version of tangent squared. Like secant squared and tangent squared have that relationship, but it's not helpful to do that because then I've got tangent squared and I don't have a way to actually do an antiderivative of that. So it's easier to leave it as it is, because what is the antiderivative of secant squared? That's actually tangent. You may be right, but even if you did, you could manipulate with it to change it into a form of tangent. It just won't end up being helpful. It'll be a form of tangent squared. Tangent squared plus 1 is secant squared, I think, is the relationship. Is that correct? So you could replace the secant squared, yeah, but it won't be helpful. Getting it in terms of tangent squared, no matter what we do, is not going to be helpful. We could get it in terms of a version of tangent squared. We just don't want to. The antiderivative of secant squared is tangent. What's the antiderivative of the 1? X. And then plus c, right? All right. What fun. We had already said that this in the front, I have continued to write it in a funny way, but it is 1 over secant, right? Yeah. So I'm going to write it that way because it's going to clean up simpler, nicer with my values. Tangent, well, is sine over cosine plus my x plus my c. And of course, what is 1 over secant? Cosine. So I have cosine of x times sine of x over cosine of x plus x plus c, which gives me what?
Sine of x plus cosine of x squared plus cosine of x times c.
You're really close, Abby. In the middle, I think you have written something where you multiplied the x's together, not in quite the right way. We're going to have x cosine of x, like that, and then plus, and this looks terrible because I've used c, but c, I'm going to put a dot times cosine of x to try and keep the c and the cosine and the c as self-separated. Yeah, lots of c's. I don't have another slide. All right, let me shrink this a little bit so that I have more space. All right, this is the equation for the general solution, which we were not exactly asked to find. We were asked to find the particular solution, and the particular solution information that we have is that y of 0 equals 1. So we know that this is going to be 1 on the left, and we're going to have x is 0. Now, a lot of these go away very nicely. What's the sign of 0? That's 0. This one's 0 times cosine of 0, so it's 0 times something, so it's 0. What's the cosine of 0? 1. So this is plus c times 1. So what is c? C is 1. So our particular solution, which was really honestly not a lot of work to find on this one, right, because we had zeros and ones, is sine of x plus x cosine of x plus cosine of x. And you can definitely leave it written that way. If I think there's a version that I had seen in an answer key on this one where they factored the cosine out at the end. I have no idea why you'd want to do that, but the version that I had seen written on this one at some point was that this is sine of x plus x plus 1 cosine of x. So if you want to do that, more power to you, but the first one's plenty enough fine. Any questions on that one?